Okay, so our next topic, we're going to talk about periodic operating point analysis and AC analysis. We're just going to hit those again in a little bit more depth. So this is topic 1.0.5. So we mentioned it before, we'll reiterate now. The periodic operating point analysis is just a specialized transient analysis. What it's attempting to do is to force the circuit into a steady state condition. And by steady state, I mean because it's switching, there's this on-off limit cycle. And what you want is you want to retrace exactly that same on-off limit cycle on every switching cycle. Okay? And so the pop analysis is actually like, it's putting a software control loop around your circuit. So here's my circuit with its, I'll call it the hardware control loop. Simplest now is going to put a software loop around all of this. And what it's going to try to do is to give every capacitor and every inductor in the system a set of initial conditions so that every cycle looks the same, one after the other. Okay. So this works because the accuracy with which we can solve the set of piecewise linear equations is so high. So now you can really tune in and make very tiny adjustments to the initial conditions and get the system into what really is a really good, solid, steady state. Once you're there in steady state, then you can get a really good AC analysis. Another thing that we'll be talking about, and we'll talk about it more tomorrow, is that Simplest looks at your circuit as a sequence of piecewise linear topologies. So, for example, when the switch is on, it's just, a resistor, an on resistor. The diode is an off resistance. And so, and now you can draw the schematic, and everything in there is a linear component until it comes time, say, for example, for the switch to turn off. Now it's an off resistor, and now the diode's on, so it's an on resistance. And so these are there's a sequence of piecewise linear topologies that Simplest is solving as it's going through, a given switching cycle. You have to have a successful pop analysis, so you need to be in steady state in order to run an AC analysis. One of the things you'll find is Simplest is almost pathologically committed to accuracy. You can't make Simplest solve this set of equations inaccurately. It just is committed. The pop analysis, it's going to work until it gets there or decides it can't get there. And we'll talk a little bit more about what that is. But every time Simplest solves the set of equations and determines, now is the time where the switch was off, now it's going to turn on. That time point, when it makes that transition, is solved to an extremely high degree of accuracy. All the time, there's just nothing you can do about it. Okay. For example, as a user, you don't have any control over time steps. Simplest controls the time steps because it insists on a level of accuracy that's quite staggering. Another thing that we'll talk about more is the AC analysis. These results are valid at this operating point, this sequence of on-off limit cycle, this on-off limit cycle where you found this periodic operating point with the pop analysis. Wherever that is, that's where Simplest is going to do an AC analysis. It's possible to have the circuit be in a state that you're not expecting. And then you get some interesting results, and we'll see some examples of that. Okay, so let's do this. Let's tidy up, close our schematic, do not save. Close the waveform viewer. All right. And now what we're going to do is go to schematic 1.2. So we go to the file view, schematic 1.2, tutorial buck. Okay. And let's go and look at our analysis. So in order to set the analysis directives that we want, you can go to Simulator, choose Analysis. You can also hit the F8 key, Function 8 key. Okay. Now, in this case, what we want to do is we want to uncheck the transient box. So we only want to do a pop and an AC analysis. Okay. So be sure that the transient button is not checked, that you have checked pop and AC, and everything else should be good. So now you can just click on run, and we will run the simulation. Okay. So now we can look at the SW, the switch node. And so here's our output voltage, load current, steady state, inductor current, steady state, and the switch node, steady state. Okay. Now we also did an AC analysis, so we can go and look at the AC analysis. And we see that. So let's talk about the pop analysis. What is actually going on when we do a pop analysis? Well, the first thing that we're doing is we're going to, every time a new switching cycle starts, we're going to look at every inductor current and every capacitor in the system. There may be capacitors, and will be capacitors in a MOSFET. There may be just the gate to source capacitor. There may be drain to gate and drain to source capacitors as well. Also, any capacitors in any subcircuit, including in this case, our compensator. So here we have 3 parts, 3 capacitors. So it's going to look at all the capacitors, all the inductors in the system, look at capacitor voltages, inductor currents at the beginning of a switching cycle. It's going to sample those and record them. And then it's going to restart the simulation and go one more switching cycle. And then when the next switching cycle starts, it's going to stop. Again, look at all the inductor currents, all the capacitor voltages. And then it's going to compare those to the values from the previous cycle. And if those are the same within a very small tolerance, then we're in steady state. We're retracing our steps. And at the beginning of every cycle, all the inductor currents, all the capacitor voltages are the same within a very small tolerance from what they were at the beginning of the previous cycle. So that's basically how POP defines steady state. It's not any more complicated than that, but that's how it does that. Okay.
But Tom, how does it get to the point? I mean, in a few iterations. You don't have to run a long sequence for. I know it's probably secretive, but
right. Well, let's go there. The first question, though, is how does it know when a new conversion cycle has started? Simplest literally has no clue what the circuit is. It's assuming that it's a switching circuit. You can, make that assumption, but it doesn't know it's a power supply. It doesn't know it's a buck or a boost or, a switch capacitor filter or a Class D amplifier. It has no clue. How does it know when a new switching cycle starts? Well, there's this schematic device called a pop trigger, and it's going to look at the output of this device. And then we have to connect the input of that device to something that in this case is going to go, let's see. Yeah, if we go up here to where we set up our analysis, pop analysis. So we're going to look at the falling edge. So this ramp generator goes up and then has a sharp edge down, goes up and sharp edge down. So on that sharp edge down, which is when typically, in this case, we're going to turn on the switch, that's the pop trigger is going to have this output go high, and then the simulator is going to look at this output, and it's going to say, oh, okay, whenever this goes high, that's when a new switching cycle starts. So then when that new cycle starts, it goes around and does the drill. What are all the inductor currents and capacitor voltages? Records those, restarts the simulation, and we do another time domain transient simulation until the pop trigger goes high again. And then it stops, again, records all the inductor currents, capacitor voltages, compares those to the previous. And that's where, the smarts happen. So it looks at those differences, and it will, in fact, we can look at that. So I'm going to do Control Shift, and that will bring my status window up to the fore here. And so what it does is, so the very first time it did this, the error was 6.6%. So the largest difference between either inductor current or capacitor voltage was 6.8%. So then it runs some more. And then at the next time the pop trigger goes high, it stops. And now, we're a little closer to steady state, but it's still 5.5% away. So what it does then is it has an algorithm. And, this isn't the subject of the course, except we are going to go into detail on how pop works, but we can't possibly go into the details of how it figures out exactly what to do. But it then, based on this analysis, it tries to predict what is the best or the better set of initial conditions for the inductor currents and the capacitor voltages in the whole system. And then, so it changes those values, reruns the sim, does another cycle, and okay, we're a little bit closer, but we're still way too far away. So it does another calculation, and then the pop trigger goes high again after another cycle of simulation. Now we're down to 2.49%. Okay, let's do it again. Oh, now we're making some progress. So now we're 0.3% is the largest error in any inductor current or any capacitor voltage between the beginning of one cycle and the beginning of the next. It does another prediction of saying, okay, let's try a new set of values for all these energy storage elements. And now we're down to 10 to the minus 5%. It does one more projection, and now we're 10 to the minus 12. So 10 to the minus 12, this is where that low noise floor comes into play. That's low. Okay, so which is why we could get away with injecting tiny signals here. Okay, so once we get to an error level that is acceptable, that meets our criteria, our convergence criteria for the pop analysis, then it declares success and now starts to do whatever is next, in which case is so it's going to calculate. So what it did here is it calculated the steady state waveforms, and then next we asked it to do, which is the AC analysis. Okay.
So if you preload the transient snapshot, that's the reason why it will converge faster to the result?
Yeah, so the closer your initial conditions are when you hit go, the closer your initial conditions for all these energy storage elements, the closer they are to actual steady state, the faster pop will converge. And so what we're going to talk about tomorrow is some of the strategies that we recommend that you can use to do that, because the faster you get to steady state, the faster you get to start doing what you really want to do. As Christoph pointed out, if doing a long transient is your only way of getting to steady state, you're front loading every simulation with a long, basically startup transient. You may not start up from 0, 0, but That's the worst you can do, is start up every simulation from 0, 0. You're just killing yourself for doing that. Because if you think in the lab, 95, maybe 98, I don't know, % of the lab measurements you do, the system starts out in steady state. You perturb the system, you measure, characterize the response, and then you go on to the next one and the next one. Almost everything that you do in the lab, you start in steady state, and then you perturb the system and then try to measure what it's doing. It's the same thing in simulation. So what POP does is allows you to get to steady state so much faster than a long transient. And that's, so getting good at POP, which, as Christoph pointed out, getting good at having initial conditions that put the system close to steady state to start with, it's just money in the bank. It's time, your time that you get back to do other things rather than wait for long transients to finally get to steady state so you can do what you really want to do. Okay, so we've talked about the status window, or we mentioned that it exists. So the status window is, if it looks like this is a dot matrix printout, that's because that's what it used to be. Back in the day, everything, including SPICE, everything was, that was the only printout you ever got of anything, was a dot matrix printout. And this has essentially remained virtually unchanged since the earliest days. And one of the reasons is it's just so useful. There's so much information. I often use an analogy. If you look at doctors, they walk around and they have a stethoscope. One end goes in their ears, the other end they poke and prod and tell you to cough or whatever. But there's no amplification. There's no electronics. It is the simplest of mechanical devices. And yet people have tried over and over to come up with electronic stethoscopes. And doctors just don't like them, because the stethoscope is magic. They get to hear what they want to hear, and it filters out the stuff they don't care about. And it's pretty cool. This is, if you want to see how Simplus is doing, how Simplus feeling about this simulation, this is the stethoscope. And if you get good at looking at it and reading it, it gives you all kinds of information, really helpful information. And we'll talk more about this. When there's certain failure modes, like if POP doesn't succeed, there's certain signatures, in the status window that I can look at the status window and almost right away tell you what the problem is, just because I can see that the status window signature. But let's just look and see what's going on. So we start the simulation. Every time it does a new topology, that's some new combination of switches, of piecewise linear components going from one piecewise linear segment to the next, creates a new topology. The diode going from on to off, switches going from on to off, all of those, each one of those creates a new topology. And so, but eventually we get to a starting point. What a starting point is this is a topology that Simplus can make sense of. Kirchhoff's current laws and Kirchhoff's voltage laws. In this topology, they're all satisfied. This makes sense. So it says a starting point's been located. Now it's just running the simulation. And every one of these is a new topology, some new combination of piecewise linear device, an on-off switch, piecewise linear resistor, piecewise linear inductor or capacitor. Okay. And then so we're doing a POP analysis. So then pass one is the first pass through the POP analysis. We'll go into a lot more detail on all this tomorrow And I think by the time we finish that, POP will make good sense to you. Because POP is such a powerful tool, if you don't understand how it works, you're really operating at a disadvantage. If you're trying to imagine what POP is doing, you'll almost always guess wrong. So having some instruction on how POP works and what it's doing is very, very helpful. And it will turn POP into something that is occasionally very frustrating to a really powerful tool that you can wield to your advantage. Okay, so eventually, so we're getting more and more new topologies. A new topology is some combination of switches and piecewise linear component segments that has not been encountered previously. All right, so then you see once we got to topology 52, we didn't encounter any more, even though we're going through multiple passes of the POP analysis where it's updating its recommended initial conditions for these piecewise linear component values at the beginning of a cycle, and then it's calculating the error at the beginning of the next cycle, recomputes and predicts a new set of initial conditions, runs the next cycle and does it again, and then finally when it gets to be a sufficiently small error of the largest error of all the changes for all the energy storage elements, then it declares victory, and now we have a successful POP run.
So Tom, quick question.
Yes. Yeah.
That means essentially that, for example, in your example here, topology 33 could be called again in pass 5 at some point, right?
Exactly. Topology 33 could be happening on every single switching cycle. It's just that, and we'll talk about this tomorrow, but there's a new topology, meaning here's a topology we have not encountered before. A known topology is one that we have encountered before. And what happens is Simplest will actually store the information, because every time we get to a new topology, you have to do some reasonable calculations. You have to invert some matrices. You got to do some math. And what it does is it'll save the results of that math. So if it ever encounters topology 33 again, rather than doing all the math and inverting the matrices, it will just say, oh, I've been to this topology. I know what this is. I've done the math already for it. It runs to memory, pulls that out of memory, and cruises along. So that's if you're doing, we don't have anything quite complicated, but if you have a relatively complex circuit like the multi-phase sync bucks, you end up encountering, and we'll talk about this tomorrow as well, but you end up countering the new topologies early on in this simulation, say like a step load transient. And then once you're not encountering any new topologies, you'll notice the simulation visibly speeds up. So it may take longer to do the first 25% of the simulation than it does the back half. The back half of the 75% will go faster than the first 25% sometimes. And you can, on step load transients, you can often see that. So Simplest actually kind of learns about your circuit. So every new topology is a new thing that it's learned about your circuit. And then it'll store that, thinking that, oh, okay, this is a repetitive system, so there's a decent chance we're going to run into this topology again, and I can save time and just do a memory lookup rather than do all the math.
Very good.
Yep, thank you. That was a great question. All right, so, and again, when we find steady state, you'll see just crazy small numbers for the accuracy that we can solve those, and that's part of the magic of piecewise linear stuff, is we can get so accurate. It lets us find steady state. It lets us do AC analysis using very, very small injection signals. So sometimes you wish, why can't I just use my SPICE model with my exponentials and my Infineon has some math, they have a set of equations to describe their MOSFETs that are mind-boggling. complicated. And sometimes people say, well, why can't you guys just do the math? Well, we could do the math, but then you would lose all of these benefits. And so in switching power applications, these benefits are really substantial. You really get a payback. And so, that's why we would argue it's worth it to figure out how to characterize MOSFETs, how to do the piecewise linear modeling, because you get really good accuracy and very fast in a very short period of time. And so it's worth it. AC analysis. We've talked about it before. Once we're in steady state, we can inject a time domain, real time domain signal into this nonlinear switching time domain system. But it's a very small signal, and use Fourier techniques by measuring the time domain of the output, use Fourier techniques to calculate gain and phase, and step and repeat. And we can do that really fast. And that's very cool. And because of the things that we mentioned earlier, we have such a high accuracy in our solution. We have a very low noise floor, very small injection signal. We just get great AC results. Our AC results are perfect. I've often bemoaned an opportunity that I missed. If I had bet $10 every time somebody did a tech support saying, hey, these AC results aren't correct that I'm getting from Simplus, they don't match typically it's typically not they don't match the lab. Typically it's they don't match my average model. But if I bet $10, just sight unseen, I would be a very wealthy guy right now just betting on Simplus, because if the time domain circuit is modeled well, the AC results are really good. Okay, what can go wrong if the POP analysis isn't successful? Then Simplus just won't. It'll refuse to do an AC analysis. So being able to find steady state efficiently, quickly, is a skill that you can develop, and we'll talk about that, in module 2. But it's a very learnable skill, and I think by the time we finish module 2, you'll get it, and then with a little practice, you can get quite good at it. Now, the other thing that can happen is you get a successful POP analysis, but the results aren't what you expect. So we can do, let me do this. I am going to go back to this circuit. And so we're going to go back to our schematic 1.1AE and the self-oscillating circuit. I'm going to run I want to do an AC analysis, so I won't bother doing, we'll do the steplet anyway. Okay, so we'll do that. And then I want to just tweak the load a little bit, and I want to compare things. So I'm going to make this be a separate analysis here, and a separate analysis here. Okay, and now what I'm going to do is I'm going to go to the F11 window. So I hit F11, or on my computer I have to do function F11, and we can see that I've set the load resistance is a parameterized value, and it's set to R load. So I'm going to change, it was 2.5, I'm going to change this to 2.0. And we'll rerun the sim. Okay, so I just changed the load ever so slightly. And look what I got. So this all makes sense. We got a zero crossing around 2 kilohertz. I just tweaked the load ever so slightly, and now my gain is in the mud. It's in the third basement, way down there, minus 70 something, 60 something dB. Okay, phase all kerplooey. Is this the wrong answer? That's the question. Is this the wrong answer? So if we go, let's look at our output voltage. We can see that with the heavier load, so this was my original output voltage. It had the same step load each time. But, voltage is a little bit less, but, it's not that bad, right? It's a 5-volt output. So the question before the house is this wrong? Is this wrong? Well, the answer is, no, it's right. And you guys all owe me $10. So I'll try to make a comeback here on the financial front. But in any event, why is that? Well, we were right on the edge of current limit at 2.5 ohms. 2.0 ohms, now we're into current limit. And so what's happening is the voltage loop now saturates. It's doing everything it can to control the duty cycle, but current limit is taking over. And so there's the response of the system to changes in the output voltage through the voltage loop are, in fact, down here. It's the system is totally ignoring what the voltage loop is trying to tell it. Now, these are both correct results. This just isn't the one you were expecting. It's not the one you wanted, but it is correct. So the point is that if your system, via the periodic operating point analysis, goes into a mode that you weren't expecting, you'll get results that look wrong, but actually are correct. So what you need to do then is look and really take a hard look at what was the steady state operating point that the system was in when the AC analysis was performed. Okay. So key points: learning how to manage POP, learning how to really use it so that you can find steady state quickly is worth so much of your time. Again, way over 90% of your simulations, of your analyses start out at steady state. So you want to get there quick. The POP algorithm only works when the circuit is switching. All right. So if your system goes into shutdown and it stops switching, then POP will fail, for example. So there's a lot of things. This system here is, doesn't look that complicated, but it's very complex. There's a lot of different modes. We just saw the current limit mode and the voltage control mode. Real systems have way more than that: over voltage, under voltage lockout, current limit, all of those things. Every AC analysis has to be preceded by a successful POP analysis. And these AC analyses are an accurate representation of the operating mode that was found during the POP analysis. All right. So you need to be aware that, make sure that it's in the mode that you expect, and make sure that, when the steady state that POP finds is in fact the steady state you want it to be in when you do your AC analysis. Okay, any questions on this?
Tom, I'd like to make a comment that
yes, please.
I think one of the areas where you can have simplest POP succeed and give you a completely wrong answer is if you do like me sometimes, you're going fast in a schematic and you mislabel a net or you leave a ground floating. Simplest is really tolerant about not having to have earth ground or rather ground, okay? And it will run. And as long as you're not causing a voltage controlled source to lose its inputs. I had one time where I mislabeled ground. Instead of calling it GND, I called it GRD. And I had next thing I had was a 600 volt output, but pops exceeded fine, and
perfect.
Right. And
everybody's
so
happy.
And I'm looking around for that, saying, how did I break this model?
Instead of charging more money on that, generating the extra energy there.
There you go.
So
Simplest. So Simplest was designed for switching power applications. We know perfectly well in those applications, and this is not a bad example, but in like a flyback, you often do a flyback because you want the primary to be isolated from the secondary. Simplest will let you model that. And if you're doing EMI, you have you have to do that. You have to, you could have one side grounded, but you need to have the other side floating. All right. And you need to very carefully manage this. But if you put a single-ended probe, so let's say here's my output voltage. This is a single-ended probe. If I put a single-ended probe on a portion of the circuit that's isolated from node 0 ground, Simplest is going to say, I can't make that measurement. In the lab, what would happen? So this is equivalent to putting a probe on a scope probe on a node and not connecting the ground clip on the probe. So if you leave the ground clip unconnected, all you see is the AC line pickup going crazy, masking anything that you might actually want to look at. Simplest will say, I can't tell you the voltage at this node because I don't know what you're trying to measure with respect to. Right. So either this has to be connected to some earth ground, which is not earth ground, node 0 ground, or we need to use a differential probe. And now we say, okay, I'm measuring the voltage from this node to this node. But there's nothing about Simplest that you don't have to have anything connected to ground and it'll be happy. Where it won't be happy is if you try to make a single-ended measurement and nothing's connected to ground. It will complain about that.